The final talk for the session is going to be from Rick Zamora, who's a senior systems engineer on the Rapids team at NVIDIA. He's going to talk to us today about NVTabular, building a Dask-based library for recommender system data pipelines. So the recording is going. So Rick, whenever you're ready, take it away.
Cool. Can you hear me?
Yes.
Cool. Yeah, sorry, I'm terrible with Zoom. All right, cool. Yeah, thank you so much for the introduction, Doug, and thank you all for being here. It's really great to be here. Thank you to the organizers for having me. So today, I'm going to be talking about NVTabular.
Oh, sorry, Rick. I think we're missing. You're sharing perhaps the wrong screen.
Yeah, of course I am.
We see a desktop background.
All right, do better. Yeah, hopefully this.
There we go. I see a title slide now.
Excellent.
Okay.
All right, cool. So before I get started, though, I do want to establish that I'm going to be talking about the integration between NVTabular and Dask. So this isn't going to be a sales pitch about all the cool things NVTabular can do and how fast it can go. Even though those things are true, the takeaway here is just going to really be, well, how did we go about building NVTabular on top of Dask? And maybe you can learn some things like if you're going to do something similar in the future. And so just in order to achieve our goal, I'm going to give a little bit of minimal background on recommender systems and then some minimal background on the NVTabular API and its origins. Then I'm going to spend the meat of the conversation talking about redesigning NVTabular for Dask. I'll do somewhat of a case study about categorify, and then we'll conclude. So first, some Rexis background. So when I say Rexis, what I really mean are recommender system models, which really are the engine of the modern internet. So the goal of a recommender system model is going to be to do something like predict the preference or rating that a user might have for some item, or similarly, maybe you're predicting the likelihood of a future user-item interaction. And when I say item, that's a pretty vague term. It could be something like a goods or content, like a streaming content on Netflix or Spotify, or it could even be another person. We're talking about like dating services. And there's this huge body of work on how do we build recommender system models that can predict these preferences really accurately. But what I'm really going to be focusing on in this talk is not this recommender system theory or recommender system models. I'm going to be focusing on the ETL side of things. So what we care about is what do typical recommender system data sets look like? What are their characteristics and what are their pre-processing needs? And so to get into that, Rexis data set, what does it look like? Well, typically, there's a lot of variation on this answer, but typically it's going to be a tabular data set with columns like brewery name, review, things like that. And the thing to keep in mind is that we can usually separate these columns, the data types in these columns into two general categories. Those categories would be called categorical, which means that the values will specify some type of group membership information. And then the other type would be called continuous. So these are features that you can usually represent in some continuous numerical form in the raw data set. So a particularly important category for recommender systems are these categorical columns, because these need to be converted into some numerical representation before they can be fed into the model. Most models cannot just handle passing in these group labels. And so you really do need to do some pre-processing. And so what do these pre-processing steps look like for recommender systems? Well, for the categorical columns, we're typically going to be using some variation on categorical encoding. We'll call that categorify in a vanilla. So vanilla categorical encoding was called categorify, but it might also be doing things like list encoding, bucketize, target encoding, and some kinds of combination or joint encoding of multiple columns. For the continuous columns, we'll be doing things typically like normalize. That would be the most common, but we might also be doing that in combination with clipping negative values or filling null values. And so something to keep in mind for both of these cases, both categorify variations and normalize variations, we're typically requiring two passes over the data set for our pre-processing operations. So the first pass would be to gather statistics like unique values if we're doing categorify, or for normalize, we need to gather things like the mean and standard deviation. And after we've made this pass over the data, then we can go through again and we can apply local row-wise transformations. So that really is the background we need about Rexes for NVTabular. So let's give a little background on what is NVTabular. NVTabular is just the ETL and data loader component of the Merlin framework at NVIDIA. So NVIDIA's Merlin framework is really just meant to be an end-to-end framework for building deep learning recommender systems. And you'll see, NVTabular takes care of both the ETL component and the data loader component. I have the ETL component highlighted here. Both of these components do, there is integration with Dask. NVTabular is fully integrated with Dask now. But in the sake of time, I'm just going to be focusing on the ETL component in this talk. And so in order to talk about NVTabular and how we integrated Dask, I think it's useful to get an idea of what NVTabular tries to do. What is the API that we're working with, both before and after Dask integration? Well, we want to do something like this. This is what it looks like now. You would start by doing something like defining a dataset object. So in this case, we're just pointing to a CSV file, but we could be pointing to Parquet files or some other table. And then once we've defined a dataset object, we would define some sort of column groups and then operations or operators that are going to be applied to that column group. So for example, the continuous columns, we might apply normalize. For categorical columns, we might apply categorify. Once we have these column group definitions, which are really just a graph of operator dependencies, then we will pass them into what we call a workflow object. That workflow object can then just use a familiar fit and transform. So it's a transformer-like model. We fit to a specific data set to collect statistics for these operators. And then when we transform, we will apply the row-wise transformation. So we'll do that second pass over the data set. And so the early days of NVTabular was really motivated by one thing in particular, and that was cuDF. Rapids cuDF, if you're not familiar with it, you can think of it just as a GPU accelerated version of pandas. You can more or less replace, PD with cuDF, and most of it will behave, as you'd expect, but everything will be accelerated by GPUs. And so cuDF makes it possible to keep your data on the GPU for the entire lifetime of something like a deep learning framework or a deep learning pipeline. So you could pull the data into disk, or so you can pull the data into GPU memory from disk, you can process the data in cuDF, and then you can pass it directly into something like PyTorch. And this can make the ETL time hundreds of times faster in some cases. And so it makes a lot of sense to try to leverage this if we can, right? The other goal of NVTabular early on was that we want to simplify the use of cuDF for pre-processing larger than memory data sets. So it's important to keep in mind, GPUs can really accelerate your workflow, but at the same time, there is limited memory resources. And this is getting better, but historically, the memory has been more limited than in CPU. And so what you really need to do for cuDF is to take just some slice of your data set, some chunk of your data set. You would read it into memory, only operate on that data set, and then pass that into your PyTorch model. And so goal number 2 was achieved by early versions of NVTabular, but the way this was done was through something called a GPU's dataset iterator. And so what we would do is we would just pull one chunk of the raw data set into memory and apply transformations one chunk at a time, iterating in a linear fashion through the whole data set. And so this is all well and good. Rapids cuDF requires all the data to fit in the GPU memory, and this early NVTabular solution that we had with using a GPU dataset iterator was working just fine. But there were some maintenance challenges, like there were limited operator support. And when we thought, okay, we have to implement more operators, this is kind of tedious. There are lots of rigid constraints on having to access the data in a linear fashion, especially if we want to collect statistics. And then there's a scalability challenge. We realized, okay, well, we can do this on multiple GPUs. We can implement distributed ETL, but aren't we reinventing what Dask has already accomplished? And so this was a real question that ultimately led us to redesign everything for Dask. And so now I'm going to go through the meat of this talk, is how did we do that? How did we redesign the original NVTabular code to work with Dask? And the answer is actually pretty simple, because at this time, Dask cuDF was also becoming very mature, or much more mature than it was when NVTabular was first developed. And so if you're not familiar with Dask-DF really is just the same thing as Dask-Dataframe, but instead of each partition being backed by a pandas data frame, now that partition is backed by a cuDF data frame. So if you have a large raw data set that's larger than memory, you could use something like read Parquet or read CSV in Dask-DF. This would be the same as using this, the equivalent call in Dask-Dataframe. It would automatically partition your data for you, and then you could use a familiar API. Would you look just like cuDF's API or just like Pandas API, which are the same. And so this improves maintainability. We can use the IO methods that already exist in Dask-DF and Dask-Dataframe. Also, we already have that Dask-Dataframe API that can achieve many of the operations that we need to perform on our Rexus data sets. And then we can also parallelize it, right? That's what Dask gives you. It gives you this concurrency that makes it easy to scale. Okay, and so now that we are going to re-implement things for Dask and NVTabular, how does this example change? Well, it doesn't. This is actually just the same slide as before. So the example, to the user they don't need to know anything about using Dask really. There is one, I guess I should highlight one little thing. There are some areas where if you are doing things in distributed mode, you do want to pass in just a client. So you would externally create a cluster and pass in a client when you're defining your data set and your workflow. And so this is what things look like with Dask, with everything rewritten to use Dask under the hood. So a data set object would take in some arbitrary external data source, maybe a CSV file or a Parquet file. It could also be an existing Pandas or cuDF data frame or a Dask data frame. It could also take in PyArrow tables. And it will also take in some column groups. So I showed earlier, you define a dependency, a graph of operator dependencies. You would pass these both in effectively to a workflow. The workflow would use toDDF, which I'll talk about in a bit, to on demand create an underlying Dask data frame to operate on. When you call fit, it will eagerly execute a collection of statistics graphs on this data frame. And then when you call transform, it will effectively call map partitions to call many user-defined operations on each partition of your underlying DDF and output a new transform data set. From there, you can write that to disk, or you can pass it into a model, a PyTorch or TensorFlow model, for example. So now I'll talk a little bit about the new dataset API after moving over to Dask. Like I said before, you would pass in a client if you want to do this in distributed mode. But the important things to understand about the dataset API is that it can accept, like I said before, a path or a list of paths. It can accept a data frame or a data frame collection. And then it has these three very important methods that can be used by the workflow or by the user. So there's toDDF, which means it can on demand generate a Dask data frame collection with a specified column selection. It has toItter, which is used by the data loader API, which is really just first calling toDDF and then iterating over the partitions of a data frame to feed it into a machine learning model or a deep learning model. And then toParquet, or the output API, so that you can write your data set to disk. And an important thing to keep in mind as well is that a big reason why we have this dataset API, I'll give some more reasons, but a big reason is that we have these convenience arguments like part memory fraction and part size. It just makes it easier for us to produce partitions of a target size, no matter what the backend is, whether it's Parquet or whether it's CSV. And for example, we're showing part memory fraction of about 10%. We want our partitions to be about 10% of the single GPU memory or smaller. And so how do we actually implement something like that? I'm not going to go into too much detail, but if you're defining a data set where it's pointing to something like a Parquet file and you specify 10%, you want your memory fraction about 10% of the GPU memory, we just do something very simple. We multiply that partition or that memory fraction by what we know to be the size of the total single process memory capacity on the GPU or in CPU if you're in CPU mode. And then if it's CSV data, we can just use the existing block size or chunk size arguments to get what we want. If it's Parquet, we have to use the split row groups right now. So hopefully in the future, this will improve. But for now, what we do is we actually sample the first row group in the data set to figure out, well, how many row groups do we expect to want in each of our partitions? And we use this rather than actually querying any of the Parquet statistics. just doing this is actually very fast, which is how we do it, and it typically works. And so you might be asking, besides the fact that I just told you that we have some convenience arguments, so why are you just not ingesting a Dask collection in NVTabular? Why don't you just say create a Dask collection, pass it into your workflow? And there are a variety of reasons for that. In the long run, it would be great if our data set API was very, very, a very thin shim layer that was not really doing much. But even right now, there are things that we do in NVTabular that are not yet accomplished in Dask. For example, NVTabular can query and save the original file to partition mapping. It can inspect the graph to do this, and reserve or store this information. And then when you write the data set back out, it can actually map those same partitions back onto the same file names or the same, or aggregate them together. And NVTabular can also use Parquet file metadata to calculate the size of your data set or your iterator without even reading any data in at all. It can just use the metadata. Dask-Dataframe can do this, but it just doesn't do it yet. And so it's worth noting, in the long run, we want to move all these optimizations into Dask itself, but it is great to have, and it's very advantageous to have this space where we can do custom optimizations and get ahead of the curve a little bit. So now we can move on to operators. What do operators look like under Dask? There are two forms of operators in Dask. When you call when you're just calling transform, you will just be using a vanilla operator, which only has really a transform method that we need to care about. If you're calling fit, it's going to be collecting all the stat operators, which have both a transform and a fit method. And then just what I want to convey here is that a transform, the logic for a transform within an operator is always just going to be operating on a particular data frame, like a pandas data frame or a cuDF data frame, because we're going to be using map partitions to group all of these user-defined functions together. When we call fit, the logic is always going to be defined on a data frame collection, so a Dask data frame collection or Dask cuDF data frame collection. And this is because we want to be able to leverage the existing Dask cuDF API for doing complex operations like median, things like that. So, speaking of median, here's a real example of a stat operator called fill median. And all this operator does is it's meant to go through and find any null values and replace them with the median of the data set. So it is a stat operator because it requires you to first figure out what the median is of your data set. And the way this works is we have an initializer where we are going to store, the statistics that we need to collect, that we need from the fit call to use during the transform call, right? And then the fit call is going to be using the Dask-Dataframe API. So here we're just calling quantile because that's quantile of 0.5 is effectively the median, or at least that's what, close enough for what we need here. And then when we call transform, we are just going to be using what we stored as the median and using that to fill every value, because this transform logic is just going to be grouped with other transform logic into a single map partitions call within the workflow. And then the fit finalize is just a way that we store the statistics between the transform and the fit. And so I've already alluded to this a few times, what is going on in the workflow, because it aligns very closely with what's happening in the operator. In the workflow, we have a fit method and we have a transform method. The fit method is always going to be collecting a list of stat operator fit graphs together, and then it's going to be calling compute on them together eagerly. So we're not creating a graph of dependencies that's then hooking into the transform graph. We're going to have two separate graphs. First, we're going to create our stat operator graphs. We're going to compute them, fill in our statistics. Then we're going to call transform. And the transform is just going to aggregate all of our transforms together and call map partitions on them. And so you can kind of get a good idea of how both of these phases work if you just look at how fit works. And this is just pseudocode. It's kind of dramatically simplified just so that I can talk through it. So when you call fit on the workflow, what the workflow is first going to do is it's calling 2DDF to on demand create a Dask data frame from your data set that you're passing in. It's going to make a column selection to allow high level graph optimizations of so you don't do any IO you don't need to do. And then we're going to loop through all of the independent phases, stat operator phases. So this will include a group of all the stat operators that don't depend on one another. For example, if you're doing categorify and normalize, those can be done in the same phase because they're usually operating on completely different columns. And then within, each of the column groups that is being operated on for this phase, first, we apply all of the transforms that are required as dependencies for these statistics. For example, if you did some kind of negative value clipping, and then you want to get the average value after that, you would have to do the transforms first, and then you can collect statistics. You see here, so we're using map partitions, right? So we're passing a Dask-Dataframe, we get back a Dask-Dataframe, we're not executing anything. But when we are collecting all of our stat operators together, we then immediately do call compute on those list of statistics. And so in order to talk to us a little bit more, I'm going to do somewhat of a case study on a specific design challenge of categorify. And so I've already alluded to it several times. What is categorify? It just means we have some kind of categorical column, and we want to convert it to a numerical form for our model, because that's what Rexus models typically require. The problem is, we typically have many variations that we might be capping by some frequency, like values that don't show up, more than 10 times, we just treat as null. And we might be doing, we might be categorifying multiple columns together. And also, like, the existing Dask and Dask-PDF APIs don't exactly capture all of these variations, like unique and group by target similar, but slightly different things. And also, if you wanted to just do the obvious approach of what would you do with Dask-Dataframe, it would probably look something like this, right? If we're looking at the graph, if we would do some IO, so this would be for 2 different partitions, we might calculate the unique values for a particular column that we want to categorify, and then we would be passing, those categorical results and merging the results to our original data set, right, to get our categorical encoding column for one particular column. Besides the fact that we typically need to do this for many columns, not just one column, there are a few problems with this. First of all, I just stated that NVTabular requires us to separate the statistic operator graph from the transform operator graph. Now, I haven't really said this, I'm noticing, but it's mostly for memory pressure purposes. Notice that this is typically a much more performant way to do things. But this, nevertheless, is the requirement for NVTabular. So how do we have to separate these two? We can't do it like this. The second problem is that, like I've already said, there are many different variations on categorify. This is only going to cover one particular case of one particular column. And a third problem to think about is that problems like this often require us to have memory spikes where we are concatenating results together within a reduction tree. And this is fine, but it usually means that we need to dramatically reduce the size of our partition, or we have to turn up spilling all the way in order to avoid out of memory errors. But it would be nice if we could just, preemptively say, hey, we are going to be spilling here. Let's do something smart about it. And so this is really the solution we came up with. First of all, we need to have 2 separate graphs. So that's exactly what you see here. We have a categorify graph where we're calculating our categories. And then we have a transform graph where we're just doing embarrassingly parallel transformations. So the second problem that I had mentioned before is that we have lots of different variations. And the way we accomplish that is really just by having our own custom graph. So this is not using group by or unique or anything like that within Dask, because we realize we need lots of different small knobs to tune. And so we ended up in this particular case, although we use Dask-Dataframe API in other places, in this particular case, it made sense to come up with our own homegrown solution. And the last thing I'll mention is what we do, since we have our own solution, what we can do is we can preemptively spill in ways that we know are fast. For example, if we know that we're going to end up spilling and unspilling over and over again during these concatenation stages, we can just move data from cuDF into Arrow, and we can concatenate Arrow tables rather than doing it in pandas or spilling and unspilling and then concatenating in cuDF. So yeah, good. All right. So in conclusion, I do really quickly, I said I wasn't going to talk about how fast it was, but it is worth mentioning and showing a simple result, at least of a simple benchmark. Here is the Criteo DLRM preprocessing benchmark that we often use just to make sure that we're not slowing anything down. We typically run it over and over again during development. And so you'll see for this particular case of this 1.3 terabyte data set being preprocessed for the Facebook's DLRM model, on using this Spark reference, it takes 180 seconds. Using NVTabular on 8 GPUs of a DGX1, it goes down to about 3 minutes. I can say that this goes down even further. It's like 2.5 minutes using Mads's most recent spilling work, but it goes even lower than that with A100. And so with that, I just wanted to conclude with a few points and say thank you guys all for being here. Rex's data sets are typically really large and complex and require complex pre-processing. And so Dask-Dataframe does provide the ideal foundation for NVTabular to simplify, accelerate, and scale these ETL pipelines. And Dask NVTabular integration is also designed to enable custom optimizations wherever possible. In some cases, we have our own dataset API so that we can get ahead of the curve a little bit, but we also implement our own API in some places so that we can apply custom optimizations. And so with that, I'll say thanks to you all, and it's also a special thanks to Ben Frederickson and even Aldridge, who are also heavily involved with the development of NVTabular, and Ben Zaitlin, who has provided a lot of support as well. Thanks.
Okay, yeah, thanks a lot, Rick, for this great talk on NVTabular. We definitely have a little bit of time before questions before the end of this session. And just a reminder for everyone, after this session, there is another one of the summit keynotes. So yeah, we have some time for questions, so feel free to drop them in the chat or in the Q&A, and we'll pass them over to Rick. So.
And sorry, I didn't realize that my video was not, of course.
That's all right. So, so far it doesn't look like we have any questions. I'll give it another minute or so before go ahead and stopping the recording and opening the room for the next session. But yeah, if you have any questions, please do. Go ahead and type
yeah, and
in.
also feel free to, I know I'm very thorough, there are probably no questions at all, but if you have any questions, feel free to send me a note on, through email or on the Slack or on GitHub, whatever works for you.
Great.
But I don't know, can you message people on GitHub? I guess that doesn't make any sense.
I mean, there's discussions now, so maybe on the NVTabular has a discussions panel. Great. Okay. Well, yeah. Thanks again, Rick, for the great talk. We will I'll go ahead and close down the recording. And as Rick mentioned, feel free to. Oh, here we go. We did get a question pop up here. What kind of level of experience would you say is needed to develop custom algorithms? Is it wizard level stuff, or do you see clients using it?
That's a great question. What I see clients being it's going to be very easy for clients to define custom transformations. It's just equivalent to like defining a CUDF or a pandas level logic. But it is true, if it turns out to be the case that it's more performant to define your own Dask collection level graph, it does require a little bit of experience and knowledge of how Dask graphs work and what is efficient. So it's getting closer to wizard level for the stat ops definitions. For just vanilla transforms, very little knowledge is required, I would say.
Great. Okay. So that puts us, gives everybody a minute or two to head over to the keynote. So thanks again, Rick.